Assalamualaikum and selamat sejahtera. My name is Kumar Firdaus. I am from Group 5 and today I will be discuss on aluminium magnesium alloys. Alloy is a combination of more than one metal or metal combined with non-metallic elements. The elements are combined usually while they are in molten state and the resulting mixture is cooled and solidified to produce alloys. In this case of study, we are required to do studies about aluminum magnesium alloy. This combination make aluminum and magnesium as the primary elements, and this alloy gain beneficial properties from the addition of magnesium into aluminum. So for its physical properties, it is low in density that make it lightweight and have a melting point ranging from 500 to 650 degrees Celsius depending on its composition. It also have good electrical conductivity that make it commonly used in electrical and electronic application, and it has high thermal conductivity that make it transfer heat efficiently. So for its mechanical properties, we can see that the addition of magnesium into aluminum improve its strength and hardness, and it has good ductility so it can be deformed without being fractured. It also have good corrosion resistance that outside layers will form on the surface of the alloy, and it is easily weldable and it can be joined using various techniques of welding.
Hey, Assalamualaikum. I am Muhammad Azrul Izmi. We'll discuss about the phase diagram. So this is our group phase diagram, magnesium aluminium alloy. We can see it on the screen. So there are three types of reaction: isothermal reaction, intermetallic reaction, and solid solution. For the isothermal reaction, it is used to describe the phase shift that occur at a constant temperature in the alloys. This treatment can alter the alloy's microstructure and properties. For the example, precipitation of intermetallic compounds. For the intermetallic reaction, the function is to attain the necessary mechanical characteristics. These intermetallic compounds must be controlled during the processing or the heat treatment. Intermetallic in an alloy may affect its strength, ductility, and the corrosion resistance. There are four effects for the intermetallic reaction: strength and hardness, high temperature stability, brittleness, and the microstructural control. For the solid solution, it is used to describe the atomic level mixing of these alloys. When magnesium atoms are substituted into the aluminum lattice, a solid solution with a face-centered cubic crystal structure is formed, resulting in a phase. The characteristics of the alloy may be dramatically altered when aluminum atoms are incorporated into the magnesium matrix through this substitutional solid solution phase.
All right, hi everybody. Here's the application of magnesium aluminum alloys. Actually, there's a lot of application, but I only chose three, which is mainly we are using automotive industry. Next, we have aerospace and aviation, and finally power tools and machinery. Firstly, the application of magnesium aluminum alloys in automotive industry. In the automotive industry, magnesium aluminum alloys are used in various automotive applications to lighten automobiles and increase the fuel efficiency. Firstly, one of the then these alloys are used in the construction of structural elements such as engine blocks, gearboxes, cases, wheels, and suspension parts. As you can see on the left side of the slide, these are the example where magnesium aluminum alloy is used on engine block and gearbox case. Alright, next we have the application of magnesium aluminum alloys in aviation and aerospace. There's a reason why magnesium aluminums are widely used in aviation and aerospace. It is because due to their lightweight qualities, magnesium aluminum alloys are widely employed in the aircraft sector. These alloys aid in reducing the weight of aircraft parts, improving performance, and enhancing fuel efficiency. The applications range from landing gear and interior structures to airplanes, frames, and engine parts. As you can see on the left side of the slide, these are the example parts where magnesium aluminum is used: aeroplane landing gear and engine parts. Alright, finally, the application of magnesium aluminum alloys in power tools and machinery. This is also example of widely used our daily use tools. Due to their low weight, magnesium aluminum alloys are used in the manufacture of equipments and power tools. The lighter weight of these metals benefits tools like drills, saws, and trimmers, making them easy to use and reducing operator fatigue. So, as you can see on the left side of the slide, it is drills and saw.
So now we go to the phase diagram for the percentage of weightage for the magnesium aluminum alloy. I have take the 23% of magnesium and 69% of magnesium. So for the transformation of 23%, the aluminum 23% of magnesium alloy is we call as hypoeutectic, as an alloy composition place it to the left of the eutectic point. During the solidification process, the liquid aluminum will start to decrease in temperature. The liquid alloy initially contains a higher percentage of aluminum that corresponding to the eutectic composition. Therefore, the primary solid phase that forms is aluminum. The formation of the aluminum phase will deplete the remaining liquid in aluminum and liquid composition shift towards the eutectic composition. At room temperature, as the liquid cools, the microstructure consists of primary aluminum. Then it is surrounded by a finely divided eutectic mixture of two solid phase, which are aluminum plus Al3 Mg2. So this is the cooling curve for the hypoeutectic, which is 23% of magnesium. As we can see, from the 650 degrees Celsius to 545 degrees Celsius, it will undergo the phase cooling, and all are liquid in this phase. And here, the primary aluminum will start the formation, and it will stop at this temperature, which is 450 degrees Celsius, for the eutectic phase nucleation occur. So at this line, the isothermal line, the eutectic phase growth, and here the eutectic phase will complete. So this is the microstructure of 23% of magnesium. We have 5 here. So for the first, all in liquid phase. Then the aluminum will start to occurs and the lamella structure will start to be created. And we get at the room temperature, we will get this microstructure. So for the 69% of magnesium, the eutectic alloys will solidify when cooled below their liquidus temperature. The alloy will solidify as a primary aluminum phase, which is solid solution, and eutectic microstructure. The remaining liquid phase reacts with the primary aluminum phase as the temperature drops. The eutectic microstructures originate from the eutectic reactions. So this is the cooling curve for the eutectic phase. As we know, in the phase cooling, these all are liquid, and at the constant temperature, the eutectic phase growth and so on. So this is the microstructure. T1, we will get all liquid, and T2, the lamella structure will start to form, and at T3, at the room temperature, the lamella structure will completely form. This is the composition and amounts of phases at one temperature. As we can see, this is at 300.
Hi everyone, let's look at the composition of phase diagram that I will be presenting today, which is 47.5% magnesium and 61% magnesium. Okay, now let's look at the solidification process for 47.5% Mg. So first of all, at T1, which is approximately at 650 Celsius, the alloy is still in liquid phase. So when the temperature decreases and reaches the liquidus line at T2, the primary gamma phase starts to form within the liquid. And then between T2 and T3, the alloy is in gamma plus liquid phase. So at T3, the complete gamma phase is formed. So when approaching T4, a small intermetallic compound phase called Al3Mg2 starts to form within the gamma. So until it reaches T5, T5 is where isothermal transformation happen. So at T5, the Al3Mg2 plus gamma phase slowly starts to convert into epsilon phase, single epsilon phase. So at the end of the isothermal transformation at T5, a complete epsilon phase is formed. Okay, at T6, the alloy remains in epsilon phase until it reaches T7. At T7, the gamma phase slowly starts to form within the epsilon phase because it is between the
epsilon and gamma region, and then until it reaches T8. T8 is where another isothermal reaction happens. So at T8, the Al3Mg2 phase starts growing inside the microstructure. So at the end of the isothermal reaction at T8, there will be only Al3Mg2 plus gamma phase, and there will be no epsilon phase. So this microstructure will remain the same upon cooling to room temperature. Okay, so this is the microstructure and cooling curve for each level temperature. So we can see here how the alloy transform from liquid phase at T1 to Al3Mg2 plus gamma phase at the room temperature. So as we can see here, the microstructure at T6, it will be the same as the microstructure at the end of T5, uh, which is the isothermal reaction. And the same goes to isothermal reaction at T8. At the end of T8, the microstructure will be same as in the room temperature. Okay, so this is the solidification process for 61% magnesium. So as we know, at T1, which is in the liquid region, the alloy remains in fully liquid composition. And when temperature is decreased and it reaches T2, which is the liquidus line, the gamma phase starts to form within the liquid. And between T2 and T3, the alloy stays in gamma plus liquid phase. And once it crosses T3, a complete gamma phase is formed. So the microstructure will remain the same even if it is cooled to room temperature. So this is the microstructure and cooling curve for 61% magnesium. So we can see here how the alloy transformed from liquid phase to single solid gamma phase. Okay, now let's look at the composition and amounts of phases at one temperature. So the chosen temperature here is 450 degrees Celsius at 61% magnesium. So at this point, we have drawn a tie line, and the phases at this point is liquid plus gamma phase. So the composition of liquid in this point is 63% magnesium and 37% aluminium, while composition of gamma is 60% magnesium and 40% aluminium. The calculated phase fraction for liquid is 33.33%, while the phase fraction for gamma is 66.67%. Okay, there are a few methods to improve the properties of magnesium aluminum alloy. Let's look into them one by one. Okay, the first method is known as the silicon carbide inoculation method. So this is basically a grain refinement process of magnesium aluminum alloy using silicon carbide. So the aim is to obtain fine grain structure. So as we can see in the picture in the right, the size of the grain in the alloy is reduced. Because when the grain size is reduced, the dislocation pile up at the grain boundary will decrease. So we need higher stress applied onto it to move the dislocation across the grain boundary. So this means that the yield strength of the alloy is increased. Okay, usually MgAl alloy that has been strengthened using this method is used to create engine components such as engine blocks or cylinder heads, typically the lightweight one because as we know, magnesium is a lightweight metal. Okay, the second method is known as the equal channel angular pressing or ECAP. So this method is usually used to produce ultra fine grained materials through different ways of deformation. So as we can see in the diagram below, the process is a billet of metal is passed through a die with two channels that intersect at an angle. So the metal will be subjected to high levels of shear stress, which causes the grains of the metal to break down and recrystallize. Okay, from this process, we know that basically the MgAl is strengthened by styrene hardening because when plastically deformed, the dislocations will move and additional dislocations will be generated. So when there are a lot of dislocations, they become pinned and tangled when they interact. So they will impede further dislocations and the strength of the alloy will be increased. Usually MgAl strengthened using this ECAP method will be used to reinforce tires or create rims because they can help improve the lifespan of tires as they are more resistant to fatigue and wear. Okay, the last method is alloying with manganese. So when this alloying element manganese combined with other impurities, it can help to moderate the corrosion of MgAl alloy. So for example, in the presence of aluminum and iron, adding this manganese will produce an intermetallic phase that will reduce the corrosion rate caused by iron. So additionally, manganese can also help to increase the strength of MgAl alloy through precipitation hardening, because when the precipitate form, the precipitate will help to impede further deformation in the alloy. Okay, not just manganese, but also other alloying elements like zirconium will be used as alloying element in magnesium aluminum to improve its properties and to be used in aerospace industries to create the wing scheme because it has corrosion resistance and high strength properties. So this will reduce the weight and improve the efficiency of the aircraft.
So next for phase diagram, I will be discuss on 70% magnesium and 93% magnesium. So this is the microstructure of solidification process for 73% magnesium. At temperature 650 Celsius, all of the microstructure is liquid. Upon reaching 500 degrees Celsius, the magnesium will start to solidify, and while undergo cooling furthermore, the magnesium particle will become larger. At temperature 4, which is 437 degrees Celsius, the microstructure will form a lamellar structure at the pro-eutectic magnesium. And upon cooling furthermore, the lamellar structure will grow and it will become like this, alternating with the gamma. Next, for the cooling curve, as you can see, above 500 degrees Celsius, all the state is at liquid. At 500 degrees Celsius, the magnesium will start to solidify, and at the 437 degrees Celsius, the magnesium will be completely solidified, and it will undergo eutectic freezing. This is where the lamellar structure will form. And upon cooling furthermore, the lamellar structure will grow until the room temperature. Next, for 93% magnesium, at temperature 650, it is all liquid. At 610 degrees Celsius, the magnesium particle will start to grow, and upon cooling, the magnesium particle will become larger, and at 510 degrees Celsius, all the magnesium will start to form, and upon cooling, the until temperature 340 degrees Celsius, the magnesium will start to grow completely, and the del- delta will start to grow inside the magnesium. This is the cooling curve for 93%. As we can see, above 610 is all liquid. At 610, the magnesium particle will start to solidify. At 510, the magnesium particle solidification will end. And upon cooling to the room temperature, the solid mixture will freezing and the delta will grow inside. Next is composition and amount of phases at one temperature. For this state, I choose at 500 degrees Celsius, where the phase exists is liquid plus magnesium. The composition of the liquid is at 73% magnesium and 27% aluminum. As you can see from the calculation, the mass fraction of the solid is at 15.79% and mass fraction of liquid is at 84.21%.
Ya, Assalamualaikum warahmatullahi wabarakatuh. I am Hazri Shaputra bin Shaizam and I will be explaining the phase diagram of 0.2 and 10% MgAl. So firstly, we go to 0.2% MgAl. Here at T1, you can see that the alloy is still in liquid phase. Then we move on to T2, you can see the aluminium particles starts to form. And lastly, at T3, the aluminium particles has completed the solidification process. Firstly, at T1, 680 degrees Celsius, it is all in liquid phase. Then when it cools down to 660 degrees Celsius, uh, aluminium particles start to solidify. And lastly, at T3, when it cools down to 659 degrees Celsius, the aluminium particle will end the solidification process. Next, we'll move on to 10% MgAl. Okay, so firstly, at T1, the alloy is still in liquid phase. Next, at T2, aluminium particles starts to form. Then at T3, we can see the aluminium particles starts to grow bigger. And at T4, we can see the aluminium particles has ended the solidification process. And lastly, at T5, the microstructures reach perfect solidification and form Al3 Mg2 alloy. So we move on to the cooling curve. Firstly, at 650 degrees, it is all in liquid phase. Then it goes down to 608 degrees Celsius, where the aluminum particles start to solidify. Then it cools down further to 570 degrees Celsius, where the aluminum particles grow bigger. Then it cools down further to 525 degrees Celsius, where the aluminum particles ended the solidification process. And lastly, it cools down to 330 degrees, where the microstructures reach perfect solidification and form Al3 Mg2. So we move on to composition and amounts of phases at one temperature. At 600 degrees Celsius, the phase exists in liquid plus beta aluminium. The composition of the liquid is at 10% magnesium and 90% aluminium. And the calculation on the solid and liquid phase fraction of the alloy can be seen as below. Firstly, we can get the intersection point of 4% magnesium and 90% aluminium, and 11% magnesium and 89% aluminium, both from the diagram. This is the intersection point. Okay, next, we just put it into the formula, which is 0.1 minus 0.11 over 0.04 minus 0.11 times 100%. We will get 14.29% for the phase fraction alpha. And then for the phase fraction liquid, we just subtract the value from 1 and times it with 100% to get the final answer of 85.71%.
So I'll be presenting on the phase diagram magnesium aluminum alloy hypoeutectic 65% and 99.5% magnesium aluminum alloy. As you can see here on this phase diagram, so this is the line here between the 60 and 70, which is a 65% and 99.5%. So first of all, I will explain about the microstructure of solidification process hypoeutectic of 65% magnesium aluminum alloy. So firstly, we will start at the T1, which is the temperature of approximately 650 degrees. So at here, so the first microstructure here, which is the T1 650 degrees, is where the liquid mixture cooling. It's the condition. This is the beginning of the mixture cooling. So it proceeds to the next phase, which is the so at T2, which is of approximately to 440 degrees, the mixture cooling will enter the gamma phase. The gamma phase, it will enter the gamma phase where, as you can see here, there is a gamma and liquid phase. So this is the combination of mixture where gamma and liquid both are in one phase. Then it continues, the process continues to the next phase, which is on the temperature 3, T3, which we can see as on the phase diagram here is exactly lies on the 437 degrees line, where there's a formation of magnesium lamellar structure, the lamellar structure of magnesium. So at this phase, there is no longer liquid. Here is where the beginning of the hypoeutectic phase nucleation. Hypoeutectic phase nucleation begins at the temperature of 437 degrees. Then it proceeds to the next temperature, which is a T4, also on the same temperature line, 437 degrees. And by that here, the formation of proeutectoid forms. Proeutectoid gamma forms here. So, and here is the where he is here, where the hypoeutectic phase complete. Then the process continues to the cooling to room temperature. So next, so first of all, okay, this is the cooling curve of the magnesium aluminum alloy. So it starts from the 650 degrees where the phase is completely is in a liquid. The liquid mixture cooling occurs and proceeds to the next phase where at 440 degrees the mixture enters the gamma phase. Then it enters T3, which is at 437 degrees, just a slightly different, where hypoeutectic phase nucleation begins. And at T4, which is also at same temperature line, 437 degrees, the hypoeutectic phase complete. Once the phase complete, it will proceed to cooling to room temperature. So this is the microstructure of solidification process, where 99.5% of magnesium aluminum alloy. Firstly, the microstructure is completely in liquid form at 660 degrees. Then it continues at 650 degrees where the magnesium particles starts to solidify. Just a slightly different between the 660 degrees and 650 degrees, just a slight different in temperature. And it proceeds to the temperature 3, which is a 640 degrees. And at this temperature, magnesium particle solidification end and the formation of particles is fully in magnesium. So it continues cooling, but it proceeds to freezing condition where the solid mixture freezing it's to room temperature. So this is so next is about composition and amounts of phases at one temperature. So I chose 440 degrees. So as you can see here at 440 degrees, the line P2 here, the phase exists as liquid and gamma phase, aluminum 65%, magnesium. The composition of gamma P1 is at 62% and 38% aluminum. So the next is the composition of the liquid P3 is at 66% and 34% alloy. Sorry, aluminum. So here's the calculation on the gamma and liquid phase fraction of the alloy. Phase fraction of gamma, at gamma the magnesium is 62% and the aluminum is 38%. So how we gonna find the fraction is need to use the formula where we can measure the distance from the line P2 to P1 as A and line P2 to P3 as line B. So this is the formula for if you want to find for the gamma, B over B plus A times 100%. So we get, so we found out here that B is equals to 1 and A equals to 3. So 1 over 4 times 100%, which is the 25%. Then the phase fraction of liquid, magnesium 66% and aluminum is 34%. So ml equals to A over A plus B times 100%, 3 over 4 times 100%, 75%. So adding both 25% and 75% is will be equals to 100%. Two things that we can conclude overall from the magnesium aluminum alloy, the microstructure of magnesium aluminum alloy. Okay, firstly, magnesium aluminum alloys are widely sought after for a variety of applications because of their combination of low density, high strength to weight ratio, outstanding corrosion resistance, and great machinability. Next, magnesium aluminum alloys are often employed in sectors including consumer products, aircraft, and automobiles. Due to their small weight, magnesium alloys are used in aerospace applications for things like aircraft frames, landing gear, and interior components. Die casting, extrusion, and forging are acceptable uses for magnesium alloys because to their superior machinability, which facilitates simple shaping and forming procedures. However, due to the magnesium's low melting point, it must be handled carefully to reduce the risk of fire and ignition. Fourthly, the magnesium aluminum alloys have the disadvantage of being, however, magnesium aluminum alloys have the disadvantage of being prone to corrosion, especially in hostile settings. Protective coatings and surface treatments are used to increase their corrosion resistance to help reduce this. Finally, in conclusion, these characteristics make them desirable materials in fields where cost effectiveness, performance, and weight reduction are essential consideration. That's all from me. Thank you.